So welcome everybody to the trial session on swampland and stream phenomenology. Our first speaker is Ivano Basile. He's going to be telling us about emergent geometry and string theory. 20 minutes plus 5.
Yeah, thank you.
20 minutes plus 5.
Yeah, thanks a lot. So yeah, here's the pointer. Great. Hi everybody. Of course, let me start by thanking Miguel for the kind invitation, and of course all the organizers, the ones that were in the room and not in the room, for the great organization of this conference. I'm really enjoying it. So I'm going to talk about basically my latest paper. You can find it, on Inspire. Put out with two students, one in Madrid, Cristiana Uffia, and Giorgio Leone in Turin. Well, now he's starting a postdoc in Pisa, but still. Good. So, by the way, I invite everybody to ask any questions. Time permitting, I sort of tried to make the seminar on the shorter side in order to have more time for this if need be. Good. So, this is a swampland session. It's supposed to be a swampland parallel session. Therefore, I'm going to begin with some obligatory remarks on the swampland. But it's really like bare bones. So first of all, I want to show off this cool picture I made a few weeks ago. So there's that. And the idea is that you don't get in quantum gravity. You don't get any potential low energy physics that you want, right? That's the whole. Well, at least a big part of the lesson of the swampland program is that not anything goes in quantum gravity. Not all possible low energy physics, possible effective field theories, particle content, interactions, and so on, can be realized. In fact, almost nothing goes. And in specific settings, there is a precise meaning of almost nothing. That's great, but even the most the most jaded phenomenologists would ask something like, okay, cool, almost nothing goes, but what does go then? What can I say about phenomenology? And of course, one thing you can one answer to this question is there are constraints to low energy physics. There are constraints on what kind of particles, what kind of interactions you can have. That's fine, but at low energies, if you just really care about the standard model and not much else, this is not super helpful, right? The statement, almost nothing goes, maybe it's not super helpful at this stage. So what I would like to focus on in this talk is this question, what does go in quantum gravity, but not applied to just what we see, but to what we will see, the new physics, right? This is the key question I would like to address here, or start addressing, right? So the idea is, what does go in quantum gravity in the sense of new physics? What can we expect to see, right? So the structure of a low energy theory, including gravity, is more or less, schematically that one. So there are, I would say, two main scales that can govern new physics. One is literally the scale of, the mass scale of whatever new degrees of freedom appear. What I will call the gap, the mass gap, right? To whatever new thing is there. And then there is a scale which can be the same or different than the gap scale, which I'm gonna call the UV cutoff of the gravitational part of the theory, namely the stuff that is sensitive to Planck scale quantum gravity effects, right? So there are these two scales, and in particular, if I really care about new physics in quantum gravity, I mostly care about this scale and how it is related to the gap scale, if at all, right? And here there are more or less two scenarios to, when trying to answer the question, what kind of new physics is there? And the first one is the sort of the generic one from this point of view, which is that this new scale is Planckian. And then we're basically screwed, right? I mean, unless we're extremely lucky or we discover some amplification mechanism of these super tiny effects, there's little hope, right, for experiments. But there is another option, and this is an optimistic scenario, of course, but there are other reasons to believe that perhaps we could live in such a universe where the scale of new physics, even of new gravitational physics, is much smaller than the Planck scale. This is a really interesting scenario because there is hope to actually test in our lifetimes, right? Of course, whatever theory in either scenario should predict anything. That's not, that's not the debate here. The point is, can we actually see it before we all die, right? And in this scenario, we can hope to see it, at least. So what are some features of this scenario? Well, for one, gravity is weakly coupled here, all the way to the UV cutoff, right? Because the couplings of gravitons are basically bounded by the ratio of these two things. And then we can ask, what kind of physics, what kind of new physics can govern such a hierarchy? And one option is that there are large extra dimensions, right? In such a way that the scale is actually the Planck scale of the higher dimensional description, which is much lower than the 4-dimensional Planck scale. So this is one scenario. This is a scenario that it lies within the effective field theory still. Another option is that the weak coupling goes all the way to a UV completion, and this requires the presence of higher spin degrees of freedom, towers of higher spin degrees of freedom. And this is a purely bottom-up statement based on S-matrix considerations. And funnily enough, string theory is this kind of scenario, weakly coupled string theory, that is. Great. So this is the kind of scenario I would like to focus on. The optimistic one, where we have a stringy description. And again, because this is a swampland session, I'm going to provide a little bit of bottom-up motivation for it. Of course, this is also a string conference, so I could just say, let me start with strings. But what I was trying to say earlier is that if the UV completion is weakly coupled, then there are constraints on possible S-matrix of gravitons, right? Now, this is not a proof that string theory is the only option by any means, but there are some interesting hints, is what I'm trying to say. And they're based on the fact that a consistent weakly coupled completion of graviton scattering must do the job at tree level. So we can just examine the rules of tree level S-matrix bootstrap, and there are some interesting constraints from causality and locality and so on that produce the presence of higher spin poles in the exchanges, and the actual amplitudes are very much restricted if we ask for gravity-like features like triple STU symmetry and that the amplitude reduced to GR in the low energy limit, stuff like that. So there is a wealth of literature here that really seems to suggest that these amplitudes kind of look like the ones predicted by string theory. Again, this is not a proof by any means, but it's a hint in my opinion. It's a swamplandish hint, if you will. And then another angle, which is the one I mostly investigated lately with the group in Munich, together with some other people elsewhere, is the angle of black holes, which are another universal feature of gravity. And in this scenario, where the cutoff is small, you can take the smallest black hole you can, the one with size cutoff scale, and it's still big relative to Planck. That's the key. So you can still apply the usual, Bekenstein-Hawking thermodynamics with little modification. And the qualitative picture that emerges is that the towers of new degrees of freedom I described here should be put in a correspondence with the microstates of these black holes, and the thermodynamics that pops out, again, I'm not going into details because it's not the point of the talk, is that the upshot of this correspondence, which was developed more in this latest paper again from the Munich group, is that these kinds of towers are not just willy-nilly, like they are constrained. The density of states of these things more or less recover the two broad classes that I said before, namely either Kaluza-Klein states of large extra dimensions, or stringy-looking towers with exponentially growing density of states. Right. So this is more or less the picture of why, from a swampland point of view, I'm going to motivate why I want to focus on weakly coupled string theory as a scenario to say something about new physics. Right. That's more or less the point. Again, if you have any questions, please just interrupt me. Cool. So let's say I hope I motivated from a swampland point of view why focus on weakly coupled strings as an arena for phenomenology, and to ask what kind of new physics we can see in the scenario in which the cutoff is small, right? The optimistic scenario. So this is the more or less, yeah, what's up?
Since you asked for an interruption, so you
I didn't ask for it.
you encouraged it. I can be loud.
Yeah, big mistake on my part there.
Can you hear me without the mic?
I can.
Yeah, good. Why did you take the lowest dimension operator in your EFT to be 0? Why did you fine tune?
Sorry,
The
which...
cosmological constant is vanishing in your...
no, it was just a schematic equation. I didn't actually do that.
That will give you another scale, right?
Yes. Yeah,
Do you
which
have
is
anything
extremely
to say
tiny.
about that scale?
Well, you know, if we care about pheno, then that scale is like a super tiny scale, right? Relative to Planck. And the idea is that there should be some link between that scale and the UV cutoff and the gap scale. Like, there should be some sort of relation that mixes this infrared scale to these UV scales that I mentioned before. And this is super interesting, and this is what the kind of thing I'm looking into right now, actually. So I'm ignoring it for now, but it is a super important problem, which, so the kind of things I'm gonna say, the punchline of this talk, you know, says there's a message I'm gonna get to soon, and including that consideration potentially can make the message even sharper because of this relation. So it's absolutely super important, but I am ignoring it temporarily, as one says. Thanks a lot. Very important point. Good. So yeah, again, I'm gonna start with weakly coupled string theory. So I'm gonna, you know, dance with the worldsheet. Great approach. It's very powerful, very constrained, and we can ask, when is the UV cutoff small relative to Planck, of course, right? When is it small? And then we can ask, what makes it small, right? This is eventually the answer to the question, what is the new physics in this scenario? What is the stuff that makes the cutoff small? And of course, one thing that is, you know, blatantly obvious is I can just take the string coupling not just to be small-ish to make sense of this approach, but like super small in a way that makes the strings themselves, the string excitations themselves, very light. And these are the new degrees of freedom that drive new physics, right? This is an obvious option, so I'm just gonna say, okay, this is one option, I'm gonna put it aside. Not super interesting because we don't see, you know, swings at the accelerators and so on. So let's focus on the other option, right? Is there another option? Yes, because in 4 dimensions, the total central charge of the worldsheet requires that there's some other stuff in the theory, right? Some other degrees of freedom of the string. And usually these degrees of freedom are like modes in the extra dimensions, right? Kaluza-Klein states, winding states, and so on. But not necessarily, right? A priori, it could be something else. And the kind of parameters that govern a limit in which these degrees of freedom are responsible for a small cutoff are just the moduli of the internal part of the CFT, not the space-time part, right? So instead of GS, I'm gonna keep GS small-ish, so I can do some one-loop analysis, but these are the MVPs, the moduli of the CFT. And I'm not going to need to assume much about these at all. I'm just gonna assume that there are such moduli, even just one is enough, and I can shove it to infinity to get some, you know, some interesting limit. That's the plan. Good. So, again, let me just emphasize again, you know, I know what you're thinking. The alternative option to light strings is just large extra dimensions, right? This is the, you know, by far the majority of the literature on this topic, I would say. But I would like to emphasize that it's not super obvious from this very broad general perspective that these extra degrees of freedom are always extra dimensions, right? There is a wealth of both perturbative and non-perturbative, you know, scenarios in which the extra degrees of freedom are non-geometric. So the punchline of the talk, this is where you can go to sleep afterwards, is that this is the general story. But when the cutoff is small because of these extra degrees of freedom, so in this particular limit, then it is going to be extra dimensions. That's the message. So the new physics, when the cutoff is small, so in the optimistic case, it's either light strings or large-ish extra dimensions. That is the punchline, okay? So even if we start from a non-geometric setting, if I can go to some limit where the cutoff is small, we recover some geometric description. That's my claim. Okay? At least that this is what the evidence points towards. Good. Now let me try to convince you a little bit of this claim, right? So how do we probe the UV cutoff of the gravitational theory from the worldsheet? Well, string theory is super cool because it gives us a very concrete recipe to compute graviton scattering amplitudes, which are the ones that control the pieces of the effective action that I discussed earlier. And one particularly simple thing I can look at is just the 2 to 2 graviton amplitude, and I can look at one particular term in the effective action when I do the low energy limit of this amplitude, which is a coefficient that is always there, even in the maximally supersymmetric case, which is the Riemann to the 4th contraction. And for our purposes, it's just like a curvature to the 4th kind of coefficient. It's by no means the unique option. It's just a proxy I'm choosing that seems to be fairly universal, right? To produce more or less the same answer in all known cases. And of course, this coefficient has been studied to death, right? In all sorts of toroidal compactifications, orbifolds, lots of stuff, even non-perturbatively in some cases, using supersymmetry. The novelty here is that we're computing the one-loop approximation to this correction in a generic internal CFT, right? So the bottom line here is that this Wilson coefficient, which you can think of just as the cutoff to the power of -6 in Planck units, right? If you work out the dimensions, this is true in any dimension, right? This Wilson coefficient is just basically a piece, a 3-level piece, which, if you only keep this piece, you get the string scale as a cutoff. And then there's the one loop piece, which is an integral over the fundamental domain of the worldsheet torus. So it's a one loop diagram, if you will, of some partition function of the internal CFT, right? Torus partition function. And there is a regulation here because of technical reasons, like if you have an amplitude and you want to extract local Wilson coefficients, you gotta separate the local piece from the non-local piece in a one loop, calculation, and there's an ambiguity there, but the ambiguity does not affect the dependence on the moduli that I care about, so no worry there. So as I said before, the limit in which the string coupling drives the show is the limit in which this term dominates, and you get like the string scale as the cutoff, right? This is, again, not news at all. But at least within the confines of this one loop description, in which I keep the string coupling small-ish enough to trust this, but the moduli are the ones that drive the show, this term dominates, right? And so my plan is to concretely to study this thing, this object, in a general CFT, right? So in the cases we know, so geometric compactifications, when I take a large volume, for example, some, let's say, p extra dimensions that open up, then this thing scales like the volume in string units, right? So the signature of emergent extra dimensions would be if this thing scaled like the volume in string units, right? And if you will, this thing, this gap mass over the string scale squared, is the spectral gap of the CFT, right? So this is the scaling that I look for, right? So a priori, in a generic non-geometric setting, this could be anything. What I'm saying is that in the limit in which the cutoff is small, I always recover this kind of scaling, even if I don't start from a geometric compactification. This is my punchline, the technical version of the punchline. So how do I see it? Well, when is the cutoff small? When alpha is big, right? So I care for big alpha when this is the term that drives the show. Again, when this is the term that drives the show, it means that the string excitations are light. I don't care about this case. So the scenario I'm interested in is when this guy diverges in some limit in moduli space, right? This is the mathematical, formulation of the physical question I was asking. So again, on fairly general grounds, it may seem quite difficult to answer this question, but there are some things we can say just using modular invariants, and then to actually get to the full answer, there is a technical assumption I'm going to make to simplify my life. So the bottom line is that using modular invariants, I will show you briefly how we can prove that the only way that the cutoff can be small is that there is a light tower of states. Right? I'm not saying Kaluza-Klein states yet, but I am saying that there is a light tower that brings down the spectral gap. So this is the first implication. Then there's a reverse implication that applies, at least we were able to prove it with some assumptions on this light tower. There's a simplifying assumption there, but under this simplifying assumption, we were able to prove the opposite, that this light tower implies a divergent Wilson coefficient, so a small cutoff, and moreover, the scaling of this cutoff is exactly the one that I claimed before, the geometric scaling. And if you're not convinced about the fact that extra dimensions are emerging in this limit, you can go read another paper that came out in the same week, more or less, by Oguri and Wang, who show that in such a small gap limit, the end point of this limit contains an actual decompactified sigma model, and these light states are actually KK states. So the meme with the astronaut pointing the gun to the other guy, like it was extra dimensions all along. Yeah, that one. So I guess my point is that even non-geometric settings quack like extra dimensions when the spectral gap is small in this limit where the cutoff is small. Okay. So let's go to some slightly gory details in the last few minutes. So how can I actually show, for example, the first claim that small cutoff, therefore divergent integral there, implies a light tower? Well, the neat trick here is that I can use the fact that this is a certain type of partition function with certain modular properties. And the regularization here basically amounts to adding this extra term just to eliminate certain divergences in the integral in a modular invariant way. It's a technical detail, but the point is I can use some bounds inside of the fundamental domain to control the behavior of this partition function just using the gap, or more precisely, just in terms of the number of states which are below some arbitrary threshold, right? And I can show that insofar as the number of states that remain under any finite threshold is finite, this thing can never diverge. The integral will never diverge. So in order to have a small cutoff, I must have a tower of states that becomes light. This is the first implication. Then the second implication, again, as I anticipated, we relied on a technical assumption which we can relax a little bit, not all the way. So this is interesting for future work, but still the assumption here is that this tower of states becomes light in a uniform way. This is the assumption. So we choose our modulus T to be large, right? And we choose it to be basically the inverse gap. 1 over the gap is T. T is large. And we say that the dependence of our states on this parameter, on this marginal coupling, is in such a way that all the light states scale like this, and everything else is heavy. This is the simplifying assumption. Under this simplifying assumption, we can derive a differential equation that is satisfied asymptotically by this partition function, and it's very reminiscent of the exact equations satisfied by the lattice sums of toroidal compactifications. Those are exact. This one is asymptotic, but it's enough for my purpose. So we can solve it. We can actually show in a Tauberian way that the integral of this, which gives me my Wilson coefficient, also satisfies a similar equation. Basically, you just kill the Laplacian part by Stokes. You get a differential equation, you solve it, and the integral scales like I claimed. Right? This is the result. So again, I anticipated that we can relax this a little bit, and we can relax it to assuming that there are light states and heavy states, and there's some other piece of the CFT which is just neither light nor heavy, and they doesn't care. So the partition function, let's say, either it factorizes like this, And then we even generalized it to like a linear combination of sectors. It's unpublished, but it's done. So this is a situation in which only a part of the CFT decompactifies, so to speak. It's a partial decompactification. And in this case, again, we can use some fancy spectral analysis on the fundamental domain. And we can basically, again, prove that there is a differential equation, and you solve it, and you get a similar result. You get essentially the geometric scaling for the UV cutoff and the geometric scaling for the gap scale, both of the pieces I highlighted in the introduction. And that's pretty much it. So, thank you.
Okay, questions for Ivano?
So when you say that you are doing it for general CFT, so are you not assuming anything about the internal CFT, or are there some assumptions that go in there?
Right, I'm assuming those technical things about how the light states behave, right? They scale uniformly.
Okay, that's the only assumption?
Sorry?
That's the only assumption that you're making?
Well, of course, there's modular invariance, compactness,
Right,
unitarity, the usual suspects. I believe this is the only thing. Then, so what I'm using also, and this is, I think, is always doable, is that because I'm separating the internal part from the space-time part, what is also commonplace in known examples is that all the fermionic characters of the CFT are in the space-time part. Mm-hmm. So the internal part is a bosonic partition function, so to speak. So when you take the canonical restriction, it's a sum of positive terms. This is the story.
So I'm asking this question because many a times when you see CFT techniques, they are developed for RCFTs, but they cannot be generalized to non-rational CFTs.
Right.
So is there any step in your analysis which assumes RCFTs? But
I don't believe there is.
Okay. That's great.
In fact, this is important because, as you know, in, let's say, a circle compactification, the CFT is rational only for very specific values. So it better not be rational.
Yeah, sure, of course. Okay, thank you.
Thank you.
Okay, more questions for Ivano?
You assume that the UV cutoff is very small, but do you have any reason to expect that to be the case, except for the fact that otherwise we're going to die before we actually see it?
So you mean from a pheno sort of point of view?
Yeah, I don't know.
Yes, I have at least a couple of ideas on that front. One relies on the fact that we see 4 large dimensions, and one relies on the fact that dark energy is very small, to comment on what Nikolai said. So the dark energy being small, the idea is that there are certain both Swamplan and information theoretic arguments. I can give you some references that basically point to the idea that a small CC means a small cutoff. I am going to, I'm working on this to make it a bit more solid. Another argument based on the 4D space-time is that there are certain there is a type of gravitational instanton that appears in the EFT whose suppression is governed not as you would naively expect by like some energy scale over Planck or over the cutoff, which means that any low energy limit makes it under control. This guy is governed by the cutoff over the Planck scale in such a way that the only way, at least that I am aware of, to make it small, to control these gravitational instantons and have a consistent EFT, is to have a small cutoff. And this only works in 4D. So I don't know how general the argument is, but it suggests me that this is a good idea.
Okay, any last questions for Ivano? Maybe I can ask a very quick one. So you have this expression for alpha, the higher derivative coefficient, which was 3-level part plus 1-loop part.
Yeah.
And you were concerned with situations where the 1-loop part was very large.
Yes.
Shouldn't I worry when the 1-loop part is large that maybe I need to consider also higher loops?
Yeah, so the idea is, of course, a good point, and this is why I try to emphasize in the discussion that I still try to keep the string coupling reasonably small. So, of course, this quantity is what I'm calling a proxy for the actual cutoff. Okay. And of course, the true cutoff will need some full resummation. But the fact that we already get what we expect at this level, I would say, is encouraging. So I wouldn't call it a proof by any means, of course, but yeah.
Okay. If there are no ultra quick questions for Ivano, that can be asked and answered in 15 seconds. And let's thank him again.
Thank you.